I welcome you all for the wireless communication lecture module. In previous lecture, we have discussed about the conventional QPSK, and then we have discussed about the offset QPSK, which is the advanced version of the conventional QPSK. So, as I have mentioned in the previous lecture, the QPSK has a phase shift of 180 degree when we are transmitting two bits simultaneously. So the 180 degree phase shifts create a non-linearity in the thing. At the transmitter end, this non-linearity will create the side lobe. So to overcome this drawback, the phase shift has to be reduced. So in a offset QPSK, we are reducing the phase shift from 180 degree to 90 degree. Okay, by providing some delay. So in this lecture, we are going to discuss about the pi by 4 QPSK. Okay, so which is also going to be reduce the offset or the phase shift. Okay, so here the phase shift between, if you are transmitting transmit two bits simultaneously, then the phase shift is restricted here is plus or minus 45 degree to plus or minus 135 degree. The phase shift is restricted in between this value plus or minus 45 degree to the maximum of plus or minus 135 degree. So by restricting the phase shift value in between them, then thereby we are increasing the performance of the modulations here. Okay. And one more advantage is the pi by 4 QPSK uses a non-coherent method of detection. It is nothing but the receiver does not require any information about the transmitter signal. Okay, for example, the frequency and phase of the carrier signal does not required at the receiver end in order to demodulate the signal. So this is called as a non-coherent detection, which is the greater advantages of pi by 4 QPSK. And the next is in the presence of fading as well as multipath channels, this pi by 4 QPSK is perform much better than the either offset QPSK or the conventional QPSK. So for fading and multipath channel, these pi by 4 QPSK performs much better than the earlier versions. So here in the pi by 4 QPSK, these two bits are in phase and the quadrature bits. Okay, so if the information bits are 1 and 1, both in phase and quadrature phase is 1 1, then obviously we are providing the phase shift of a pi by 4. Okay, if the information bits are 0 and 1, then we are using the phase shift of a 3 pi by 4. If both in phase and quadrature phase components are 0, then it is we are using a phase shift of a minus 3 by 4. And if it is a 1 0, okay, obviously we are using the phase shift of a minus 5 by 4. So with the help of providing these phase shifts, okay, at the maximum phase shift of we are providing 135 degree. So this is the constellation diagram which ensure that there will be a 5 by 4 and a 3 pi by 4 phase shift between the bits. Okay. Next is we are going to discuss about the how pi by 4 QPSK transmits the information from the transmitting end, and then we are going to discuss about how the pi by 4 signal will be received at the receiving end. Okay, so the first is we have information bit. The information bit is denoted as a MK, which is provided into serial to parallel converter. The output of the serial to parallel converter, it separates the in phase component and the quadrature phase component. So which is denoted over here as MI of K and MQ of K. That is in phase is denoted as I and quadrature phase is denoted as EMQ of K. And then this MI K and MQK is provided input to the signal mapping. Here, the amplitude of IK is amplitude of Ik is provided in terms of cos q of k signal, and then the quadrature phase component is amplitude of the qk is multiplied in terms of the sin q of the signal. So the signal is mapped, this Ik in phase component is mapped with the cos terms, and then the quadrature phase component is mapped with the sin terms. This Ik and qk is given represented as here. K is represented in terms of cos qk, okay, which is equal to, this can be derived from the in phase and quadrature phase component of the previous equations. Okay, ik minus 1 past values. Okay, ik minus 1 minus qk minus 1 of sin qk. And similarly the quadrature phase component are in terms of sin qk, which is also taken from the positive values. Okay, so normally the theta k sin theta k is equal to theta k minus 1 plus phi k. That's this is phi k will provides the phase shift value. Okay, and after dividing the in-phase and the quadrature phase component, these are separately given to the low-pass filter, and then it is given to the modulator, where this in-phase component is modulated with cos omega ct signal, and the quadrature phase component is modulated with the sine omega ct. So the low pass filter and modulation will occur separately for the in phase as well as a quadrature phase component. After the modulation, finally, these in phase and quadrature phase components are combined with the summer, and then it has to amplified. So this is at the transmitter end. So this is the transmit. This signal has to be transmitted. We have a in phase and quadrature phase component. These are combined together and transmitted from the transmitter end. Okay. So the I of t is separately denoted over here, and then Q of t is separately over here. This P denotes the pulse shaping function, and then this Ts denotes the symbol period. So this is at the transmitter end. So, and then there are three types of QPSK demodulation detection techniques. Okay, so one is baseband differential detection and IF differential detection, and then frequency discriminator FM discrimination detection. So these three detection techniques are used to receive the pi by 4 QPSK signal. We will discuss one by one in this lecture. First one is baseband differential QPSK signal. So here the input signal what we have transmitted at the transmitter side, the string pi by 4 signal will be received over here, and first it has been given to the band pass filter. So this band pass filter will divides the in phase component and the quadrature phase component. It divides the received signal into in phase and the quadrature phase component. Okay, and then this in phase component is again multiplied with the cos omega, and then the quadrature phase component is multiplied with the demodulated with this minus sin omega. So this process is there we have a modulated signal. Over here at the receiver side we are demodulating the signal with the help of cos and the sine signal. Then it has been applied to the local low pass filter. Okay, so the low pass filter is tuned to the wk in terms of a in phase, and then it will be tuned to zk in terms of a quadrature phase. So after the low pass filter, these in phase and quadrature phase components are given to the differential encoding block. This block wk minus 1 plus zk minus 1, this block is called as a differential encoder block. So with the help of this it derives the escape from the received in phase component signal. Similarly, this it derives the yk, okay, from the quadrature phase component. So we are finding out xk and yk from the received in phase and the quadrature phase component using this differential encoding block. So after this xk and yk will be given to the decision device whether to find out whether the received bit is 1 or 0. If the xk is greater than 0, then the SI value will be of 1. If the xk value is less than 0, then the bit is considered as 0. Similarly, over here, if the yk is greater than 0, then the SQ value will consider as a 1. If yk value is less than 0, obviously it will be considered as a 0. So these x, I and SQ in phase and quadrature phase components are again multiplexed. Okay, and then it will be given to this output. So finally we are getting the signal which has been transmitted at the transmitter end. So this is the baseband differential detection. Here with the help of band pass filter we are dividing in phase and quadrature phase component, and then we have demodulated, and we have a differential encoder block which decides the in phase and quadrature phase components separately. Finally, we have a decision device which is used to detect whether the received bit is 1 or 0. Okay, this WK and ZK is given over here. Similarly, the XK and ZK is in terms of WK and ZK. Okay, and finally, this will be of received signal. As I have mentioned, xk is greater than 0, it will be considered as bit 1. Less than 0, it will be considered as bit 0. Similarly, it is similar to the quadrature phase components also. Okay, and the second method is IF differential detection. The only difference between this baseband differential detection and IF differential detection is that here we are removing the local oscillator. Normally, there we are used local oscillator to create a cos and sine signal. So instead of that, we are using a time delay is used to create the sine and cos signal. Okay, a single signal is used with the help of time delay. We are creating that sine and cos signals. This is the difference between all the other functionalities are same with respect to the IF differential detection and the baseband differential detections. Same, the decision will decide whether the received bit is 1 or 0, and finally these two in phase and quadrature phase component are multiplexed at the demodulated output. Okay, this is the second method of demodulation. And then the third method of demodulation is FM discriminator detection. Okay, so here the first the received Y before QPSK signal is given to the bandpass filter. So the bandpass signal is filter is matched with the transmitted signal where it is transmitted at the transmitted end. And then we have a limiter. This limiter is to remove the envelope fluctuations. Normally it has been transmitted, in wireless. In case of any fluctuations, that has to be removed with the help of a limiter. And then the signal is given to the FM discriminator. Here the FM discriminator extracts the frequency deviation of the signal, frequency deviation of the received signal. Okay, and then we have a integrate and dump. It is used to extract the phase difference. So the FM discriminator used to detect the frequency deviation, and this integrate and dump flags used to detect the phase deviation of the signal. So we are deriving phase deviation and the frequency deviation of the signal. Finally, we are giving these two threshold level detector. This threshold level detector will detects the signal based on the phase difference, and it divides the signal into in phase component, and then that has to be divided as a in phase component and quadrature phase component in the parallel and serial converter. Finally, the received signal will be received at the demodulated waveform. Okay, so this is about the FM discriminator. So here we are removing the frequency deviation and phase deviation, and then with the help of this four-level threshold detector, we are divide the signal into in phase component and quadrature phase component. Finally, it has been combined together as a received signal. So this is the all about 5 by 4 QPSK. So 5 by 4 QPSK has the advantage, greater advantage than the earlier versions of QPSK. It restricts the phase shift between plus or minus 45 to plus or minus 135 degree. It is used as a non-coherent detection. There is no information or carrier signal information is recovered at the receiver end. And then the in phase and quadrature phase components are, if it is 1 1, then we have a pi by 4, and then 1 0 with respect to 3 pi by 4. Similarly, 0 0 is minus 3 by 4. With respect to these are the phase shift. So this is the constellation diagram which we used in the pi by 4 cubic signal. And then we are discussing about the transmitter. We have a in phase and quadrature phase components are modulated individually and then combined and then transmitted. The receiving end, we have a three detection technique. So all these things will be receive the signal, and then separately we are demodulated. Okay, and then we will take the decision view based on the bits zeros and one. Finally, it has been combined with the help of multiplexer and be given. This is all about QPSK. We'll discuss in the next module. Thank you.